Hi, everybody. Hope you guys are all doing okay. It wouldn't be the beginning of class if I didn't ask you how everyone was doing. So hopefully you guys are all hanging in there trying to, receive all the various content from your different classes online. So as it relates to art class, I wanted to start today's lecture. So today in theory is Monday, but I wanted to start today's lecture picking up where we left off on Friday, which was we were looking at these three different hydration reactions and trying to compare them. So I have gone ahead and drawn the products of each one of these different hydration reactions, and then you'll see in red, I have made some notes about, any unique features of each one of these reactions. So the first reaction was acid catalyzed hydration, and you can see we went through this secondary carbocation and then did the rearrangement. And then following the rearrangement, we ended up with the tertiary alcohol. So, to highlight some aspects of this reaction, we obtained Markovnikov's alcohol, but as we're going through the carbocation, we should anticipate rearrangements. The second reaction, oxymercuration reduction, remember that we go through or we obtain Markovnikov's alcohol, but there's no carbocations, so therefore there are no rearrangements. So in this case, we end up with this racemic mixture of alcohols at the more substituted position of our alkene. And then lastly, we have hydroboration oxidation, wherein we obtain anti-Markovnikov alcohols. And so we've predicted the product here, and you can see we obtain this primary alcohol. And remember with hydroboration oxidation, this third reaction, that if we were generating new chiral centers, we would see syn addition of H and OH. That's not relevant in this particular example, but could be if you were generating chiral centers. None of the other three reactions, namely acid catalyzed hydration or oxymercuration reduction, had any stereospecificity, in the final product. So the hydroboration oxidation was unique in that way. Okay, so we're going to change gears a little bit now in class, and we're going to introduce a type of reactions called oxidations and reductions. So before we talk about specific oxidations and reductions of alkenes, I just want to introduce kind of from a carbon organic standpoint how we could recognize oxidation versus reduction reactions. Okay, so let's go ahead and do that. So we're talking about oxidation and reductions. Oxidation and reduction of alkenes. Okay, so first, let me just give you a brief synopsis of what we're going to look for in an oxidation reaction. Okay, so you might have, think back to your Gen Chem acronyms, and you would say, Leo the lion says GR, right? So Leo was oxidation, and it stood for a loss of electrons. Okay, so loss of electrons. But what does that actually mean from a carbon standpoint? Okay, so as it relates to carbon, generally we could think about oxidation when we change the bond to carbon from hydrogen to something that's more electronegative. Specifically, we'll be looking at oxygen. So from a carbon standpoint, we're going to be looking for the addition of oxygen to carbon, or conversely, the removal of hydrogen from carbon. Okay, and then reduction is basically the opposite. So reduction reactions, that was the GR part of Leo the lion, but it was a gain of electrons. Okay, and from our organic molecule carbon standpoint, then what we're going to be looking for is the removal of oxygen from carbon, or the addition of hydrogen to carbon. Okay, so before we actually look at the specific reactions of alkenes, I want to go ahead and just look at some generic reactions and try to think about if these are oxidations or reductions based on the criteria that we just set out. Okay, so our first example is this. Okay, so as you're looking at this, I want you to think about your functional groups that we learned. So we're taking an aldehyde and we're going to a carboxylic acid. Okay, so as it relates to this carbon, okay, think about what's happening. I'm basically replacing the hydrogen with an OH. So I'm both removing hydrogen and adding oxygen relative to that carbon. Okay, so as we go from an aldehyde to a carboxylic acid, then would you expect that to be an oxidation or reduction based on the criteria? Okay, so as I mentioned, we're replacing hydrogen with oxygen, so this would be a oxidation. Okay, so let's go ahead and look at another example. Oh, I'm still in highlighting tool. So this would be oxidation. Let me just rewrite that. Okay, so the next example then is, what if we took that same aldehyde and then wanted to consider a reduction reaction? So what would be the product of the reduction of an aldehyde? Well, let's think, relative to this carbon, how could I add hydrogen or remove bonds to oxygen? Well, think about what functional group that would correlate to. So that would be in alcohol. So notice there's 2 hydrogens now at that carbon, where before there was only the 1 hydrogen. Okay, so we've really increased the number of bonds to hydrogen at that carbon. And so this would be an example of a reduction. Okay, so that's all fine. That's related to aldehydes, but we're in the chapter of thinking about alkenes. So let's think about what might be an oxidation or a reduction of an alkene. Okay, so the one example for alkenes I want to look at is the conversion of an alkene to an alkane. Okay, so think about what we're adding across the carbon-carbon double bond as we go from alkene to alkane. So pay close attention to the hydrogen count at those carbons. We've essentially added hydrogen across our carbon-carbon double bond. Okay, so as we're adding hydrogen to carbon, we would see this as a reduction. Okay, and we'll see that actually hydrogen, H2, hydrogen gas, is the reductant in this reaction. We'll learn this reaction here in a little bit. Okay, so we're going to break up our reactions in this section to oxidations and reductions, and we'll start with oxidations. We'll have 2 oxidation reactions and 1 reduction reaction to consider. Okay, so our first oxidation is going to be OSO4, and I'll define that reagent here in a second. So this is OSO4 oxidation, and we will remember this in that we're going to form, so the formation of syn. Okay, so that's telling you something about stereochem of syn diols. Okay, so let's break down that word diols for a second. So that OL ending is telling us that we have an alcohol, and that di prefix is telling us that we have 2 of them. So, put all that together, syn diols, I'm forming 2 new alcohols, and they are related syn to one another. Okay, so let's do what we do when we first introduce a reaction and look at the general reaction conditions that afford the products of the reaction. Okay, so in this case, we're going to use OSO4, that's osmium tetroxide. I'll give you its structure here in a minute. We only need that in a catalytic amount. We'll have H2O2, hydrogen peroxide, as our stoichiometric oxidant. Okay, and then we have water. Okay, so just to think about the products then, we're going to form syn diols. So there's no stereochem really in this example because I have these generic substituents, but we'll try to show them as syn. Okay, so here is our syn diol. Okay, so syn, same side, diol, 2 alcohols. And that's the product of this reaction. So this is a stereospecific reaction. Okay, so it's stereospecific in that both OHs, OH, are added syn. Okay, so I want you to think about the previous reaction that we learned to be syn. So that was BH3 and its addition across an alkene. Remember that we afforded syn addition because we had this single step concerted mechanism where both new bonds to the carbons of the alkenes formed at the same time from the same reagent. So they had to come in from the same face. We're going to see a very similar thing here in this reaction. Okay, so let me give you the structure of OSO4, and then we'll think about this issue of syn addition. Okay, so OSO4 is osmium tetroxide. Okay, so as the name implies, I have osmium and 4 oxides, or 4 bonds to oxygen. Okay, so it looks like that. If you were to look at osmium in the periodic table, it's a transition metal, and so we have d orbitals that we can utilize, so we shouldn't be concerned about the number of bonds to osmium, although it looks a little bit off. Okay, so let's go ahead and look at an example and try to rationalize syn addition. Okay, so in our example, let's take this alkene. Okay, so here we have cis 2-butene. Okay, and we're going to react it with our catalytic osmium tetroxide, and we'll talk about the role of it being catalytic here in a minute when we talk about the mechanism, H2O2, and water. Okay, so if we wanted to rationalize syn addition in the products then, we could draw our carbon chain in the same configuration, and then we would add our two OH groups syn. And in this particular case, this is meso, and so we don't need to think about addition of the syn diols from either face because that would be the same molecule. And so we would get one meso product in this example. Okay, so let's talk about the mechanism using this reaction as our example. Okay, so let's go ahead and put in our alkene and then draw our osmium reagent. I think I need to give myself a little bit more room here, so let me drag this down. Okay. Okay, so in this reaction, what we're going to see is both new carbon-oxygen bonds form at the same time in a single step concerted mechanism. Okay, so what that's going to look like from a mechanistic standpoint is we're going to have our alkene attack one of the oxygen atoms. Then we're going to donate electrons into osmium to free up another pair of electrons on the other oxygen. Okay, so we have a single concerted or a single step concerted mechanism here. Okay, and this doesn't get us all the way to the product, but it accounts for the observed stereospecificity. Okay, because both of those new bonds to oxygen, okay, so both of these oxygens are being delivered to the alkene at the same time from the same osmium reagent. Therefore, they have to come in from the same face. Okay, so then let's just imagine that the osmium approached from the top face, then what we would see then is this intermediate. Okay, so we have our two bonds to oxygen. They're still bound to osmium. Okay, and so again, since these two new bonds to oxygen are forming at the same time and they're coming from the same reagent, they have to come from the same face. Okay, so this intermediate has a name. It's called the cyclic osmate intermediate. Okay, and again, this is the step that's responsible for the observed stereospecificity. Okay, so what happens next is not as important as it relates to the mechanism, dictating the stereochem. So everything else is really just cleaving those osmium-oxygen bonds and then regenerating our catalytic OSO4. Okay, so I'm just going to abbreviate this as hydrolysis, and the mechanism here we're not going to worry about. So H2O hydrolysis. Okay, we haven't seen that word yet, hydrolysis. So what it basically means is we're going to use water to break bonds. Okay, specifically, we're going to use water to break the osmium-oxygen bonds to free up our diol product. Okay, so then the product of hydrolysis then is going to be our syn diol, okay, so our product of interest. And then the other thing that we generate in that step is going to be this osmium species. Okay, and you'll notice that this is not the same osmium species that we utilized in the first step of the mechanism, because two of those, osmium oxygen bonds are single bonds. And that is the role of H2O2. So H2O2 then is going to regenerate our active oxidant species OSO4. Okay, so that's the role of H2O2, and we're not going to talk about that mechanism to any length. Okay, so you might be wondering, well, why not just use, stoichiometric osmium and not worry about the H2O2 step? Well, osmium is super toxic, and so it's not trivial to work with, and so we try to minimize our exposure in using these toxic chemicals. Okay, so just to reiterate a few of the key steps, that we're forming both new carbon-oxygen bonds at the same time from the same face, so we get a syn diol. So let's go ahead and just look at an example or two of this reaction. So we'll do one cyclic example, maybe this cyclopentene. And again, our conditions are OSO4. We only need a catalytic amount of that, H2O2, H2O. Okay, and so then in the products, in this case now, when we think about our syn diols, we don't have a meso product here. So we have to think about the fact that OSO4 could approach the alkene from the top face or from the back face, and so we'll get this racemic mixture of syn diols. and this is racemic. Okay, so one last example then. Let's go ahead and consider a linear alkene. Let's try to think about one where we've generated 2 chiral centers, something like that. Same reagents, OSO4, catalytic, H2O2, and H2O. Okay, so what I would do in this case is similar to what you would do for if you were predicting the products of any other stereospecific reaction, is to first redraw your carbon chain in the same configuration that your alkene was in, and then you can add your groups by syn addition. So we'll have OH on a dash, OH on a dash, so that's the one stereoisomer, and then the other stereoisomer we would have is both OHs on wedges. Okay. So that basically highlights OSO4 reaction. We've looked at an example of a cycloalkene and a linear alkene and seen syn addition. Okay, so the next oxidation reaction that we want to talk about is something called ozonolysis. Okay, so ozonolysis. Okay, so we just introduced that term lysis for something else, right? So lysis means breaking bonds. So ozonolysis means we're using ozone to break bonds. Okay, so let me show you the overview of this reaction, and we're not actually going to look at the mechanism of this reaction at all, and so really our goal is going to be able to predict the products here. Okay, so here's our alkene, and I'm going to distinguish or try to indicate that each one of these R groups is different. So we'll have R1, R2, and R3. Okay, so the reagents for this reaction, it's a net 2-step reaction where we have ozone, okay, and then we have a molecule called dimethyl, so CH3, 2S sulfide, dimethyl sulfide. Okay, so here is ozone, and then this is dimethyl sulfide. And so you might see this abbreviated as DMS, dimethyl sulfide. Okay, so what happens in this reaction is we actually oxidize both carbons of the carbon-carbon double bond, and at the same time we cleave the carbon-carbon double bond. So this is one of only a handful of reactions that you'll learn this semester and in Organic 2 where we actually break a carbon-carbon bond. And in this case, we're breaking both the sigma and the pi bond. And when we break those bonds, we also oxidize up to the corresponding carbonyl or carbon-oxygen double bond. So let's go ahead and do that. And I'm going to try to keep the R groups in the same relative position that they were in the starting material. Okay, so we actually get 2 products out of this reaction because we cleaved the carbon-carbon double bond. Okay, so I want you to think about what functional groups you're seeing now. Okay, so we've oxidized both carbons to the corresponding carbonyl. So in this case, we've gotten an aldehyde and a ketone. Okay, so depending on what our R groups are they hydrogens or are they carbon-based groups? And this hydrogen that's right here, this hydrogen here could also be an R group. And so depending on what the substitution of our alkene is, we will end up with either 2 aldehydes, 2 ketones, or a mixture of an aldehyde and a ketone. Okay, so as I mentioned, we're not going to talk about the mechanism of this reaction to any detail, so I want to go ahead and just look at a few examples. All right, so our first example is here. So there's our alkene. Let's go ahead and write out our reagents, which is ozone, and then dimethyl sulfide. Okay, so what I would do is first identify the carbon-carbon double bond, and then think about cleavage of that double bond in terms of, what fragments are you going to end up with. So each carbon of the carbon-carbon double bond ends up with a carbonyl. Okay, so I want you to think about then, let's go ahead and count this carbon chain. Okay, and I'm just trying to count so that I can talk about these carbon atoms. So carbon 3 has 1 carbon-based substituent and 1 hydrogen, whereas carbon 4, the other side of the double bond, has 2 carbons attached. So what functional groups do you think are going to be formed when we cleave that carbon 3,4 double bond? Okay, so hopefully the answer you came up with was 1 ketone and 1 aldehyde. So carbon 4 will end up as this cyclohexanone, this ketone, and then carbon 3 ends up as this aldehyde. And I'll try to, again, draw them, so that the carbons are kind of in the same orientation they were in the starting material. Okay, so there's one example. The next thing I want to do is think about, okay, so we've seen examples where we've cleaved a carbon-carbon double bond and ended up with 2 products. Can you think of any way wherein you would end up with a different number of products? Okay, so for example, is there any way to arrive at only one product within this, after ozonolysis? All right, so there's a few ways that this could happen. One could be if the alkene was symmetric, then you would just get 2, moles or, 2x of the same carbonyl species. The other way is, what if we took this reaction and performed it on a cycloalkene? Okay, so here we have ozone and we have dimethyl sulfide. Okay, and when we cleave this carbon-carbon double bond, they're still attached through the rest of the carbon chain. Okay, so I'm going to cleave the bond between 2 and 7 directly, but carbons 2 and 7 are still connected through carbons 3, 4, 5, and 6. Okay, so in this case, we would only get one product overall, but that one molecule would have 2 carbonyls, one at carbon 2 and the other at carbon 7. Okay, so one way we could get the products of this reaction is to get our 7 carbon chain down. Okay, and then we can fill in our carbonyls. So we had a carbonyl at position 2, that's a ketone, and then at position 7, that would be an aldehyde. Okay, and so then, back to my original question, which was how could you get a different number of products other than, 2? So imagine you had 2 alkenes within one molecule. That could give you the case, that would give you the situation where you could end up with more than 2 products, because if you cleave both carbon-carbon double bonds, then you could end up with 3 products in that way. And there are some examples of that in the textbook that you might want to take a look at. Okay, I'm going to take a pause here for a second, and I'll come back and we'll talk about the reduction. All right, everybody, I'm back and ready to talk about the reduction of alkenes. Okay, so let's talk about reduction of alkenes. Okay, so we're going to only take a look at one reaction, and that has a name, generally called catalytic reduction. And this is the one I alluded to at the beginning of lecture when we introduced oxidation and reduction. Namely, this is the one that uses H2 gas, but it also needs a catalyst to help speed up that reaction. Without the catalyst present, you would be looking at really high pressures of hydrogen, which is not a trivial thing in the lab to afford. Okay, so let's look at the overview of this reaction. Okay, so here's our generic alkene, and our conditions are going to be H2 gas and some catalyst, and I'll define what that can be here in just a second. Okay, and the products of this reaction are going to be an alkane, but this is a stereospecific reaction. Okay, so we can see that H2 was added across our carbon-carbon double bond. Okay, but it turns out that this is a stereospecific reaction. Okay, and it's stereospecific because the 2 hydrogen atoms from H2 are added syn. Okay, and that's because, well, they are added at the same time from the same molecule of H2. So H2 is added syn because both new carbon-hydrogen bonds are formed at the same time and therefore must come in from the same face. Okay, so the catalyst for this reaction is one of 3 transition metals: palladium, platinum, or nickel. Okay, so you could have any one of these 3 transition metals. Okay, and we're going to think about these transition metals as like a delivery service. And so palladium, for example, can take hydrogen gas from solution and deliver it to the alkene. Okay, and this speeds up the reaction by lowering the activation barrier so that we can use, reasonable pressures of H2. So for example, when I was in grad school, I ran several of these reactions, and literally how we delivered H2 into our reaction flasks is we would fill a balloon with H2 gas from a hydrogen gas cylinder, and then we would basically stick a needle on the end of our balloon and allow it to bubble through our solution, our reaction that we were performing. Okay, so using a catalyst allows us to, use reasonable amounts or pressures of hydrogen gas. Okay, so I want to look at a few examples of this reaction. Again, we're not looking at the mechanism here, but I want to look at a few examples so that we can rationalize syn addition. Okay, so like other reactions of alkenes, we'll look at one cycloalkene and one acyclic alkene. Okay, so let's look at this example. Okay, so like our other reactions, you might just think about what the products are. So in this case, we're going to add 2 new bonds to hydrogen across the carbon-carbon double bond. Okay, and so in this case, actually, I meant to think of an example where we did generate a chiral center, but in this case, we actually don't. So in this case, that was a pretty trivial example. When we add hydrogen to both of these carbons of the alkene, we end up with that alkane product. And we haven't generated any chiral centers there. We have an internal plane of symmetry that we can see here. And so this is the only product that we need to include there. Okay, so let's try to think of then a cycloalkene example where we do generate a chiral center. So we could do something like this. Okay, so I just chose palladium. And then this example also show us the syn addition. Okay, so if both hydrogens are coming in from the same face, that would mean both methyl groups at those positions would also be pushed in the same face. And in this particular example, we ended up with this meso product. But if we had other substituents or other chiral centers present, we would get a mixture of stereoisomers. All right, so let's go ahead then and look at one example of a linear alkene, and then we'll talk about one related issue to the catalytic reduction of an alkene. Okay. So like other stereospecific reactions, what I would do is draw the longest carbon chain in the same configuration that it was in your starting material. And then I would go ahead and add the H's syn. So in this case, it would give you both methyl groups on a wedge because both hydrogens would be coming in from a dash. So you might be thinking, well, is this meso? Well, right now we can see that we're in a staggered conformation, and so there is no potential for a plane of symmetry between the 2 central carbons. So in this case, we would have to then go ahead and draw the other stereoisomer. Okay, so up here we were looking at the E alkene, right? If you were to repeat this on the Z alkene, you should get just one meso product, and so you should try that at some point. Okay, so we can use some information from hydrogenation or the addition of hydrogen gas across an alkene to assess the stability of our alkene starting materials. Okay, so let's go ahead and talk about the stability of our alkene starting materials. So stability of alkenes. Okay, so just like, any other molecule we've talked about, there's a gradient in terms of stability for one reason or another. And it turns out that we can measure or indirectly measure the stability of an alkene by thinking about the heat of the hydrogenation reaction. Okay, so what do I mean by that? Okay, so we're going to take our alkene and we're going to do our reduction. Okay, and in this case, we're just using H2 gas at high pressures without a catalyst. And so we're doing like bomb calorimetry, which you might have done when you were back in Gen Chem. And we're going to measure the heat evolved in this reaction. Okay, so we're going to add our hydrogens across our carbon-carbon double bond. Okay, and this ends up being an exothermic reaction. Okay, so it's exothermic, meaning that energy is given off. Okay, and the amount of energy that's given off is related to the stability of the alkene. Okay, so amount of heat evolved related to the stability of the alkene. Okay, so basically what we can do then is, take several different alkenes, run this hydrogenation reaction, and then compare the amount of heat that's given off. Okay, so I just want to look at two quick examples that highlights this. Okay, so what we're comparing is the delta H of hydrogenation, the difference in energy between the products and the reactants of the hydrogenation reaction. Okay, so if we were to look at these two examples, okay, so we're going to look at ethene, and we're going to compare that to a tetrasubstituted alkene, where each one of the carbons of the double bond is attached to two methyl groups. Okay, so this would be a tetrasubstituted alkene, where we have 4 substituents around the 2 carbons of the alkene. Okay, and so we would go ahead and run this reaction and measure the delta H sub H, okay, in kcals per mole. Okay, and so since this is an exothermic reaction, we have negative delta H values. So it would be negative 33 for ethene and negative 27 for this tetrasubstituted alkene. So 2,3-dimethyl 2-butene. Okay, so I want to look at the reaction coordinate diagram of this exothermic reaction just to get an idea of, how is that delta H related to the stability? Okay, so we have energy on one axis and the reaction progress on the x-axis. Okay, so what we're measuring is the delta H, okay, the difference in energy between the reactants and the products. Okay, so think about how we would get a smaller value for delta H. That would bring down the energy of the starting material. That would be a smaller delta H sub H. And so when we have smaller delta H, so when the absolute value of our delta H is smaller, that's indicating that we have a more stable alkene starting material. Okay, and that's because we've lowered the energy of the starting material like we did here. Okay, so in this case, we've lowered the energy of our starting material. That decreases delta H. And remember, lower energy is more stability. Okay, so when we're comparing these two values, we can see that the tetrasubstituted alkene, where we have 4 substituents around our 2 carbons, is the more stable alkene. Okay, so I want to just write 2 factors about this, and then I'm going to give you the general trend in alkene stability. So we can just see in this one example that the tetrasubstituted alkene is more stable than ethene, which has no substituents. So is that a general trend, or is that coincidental to this example? Okay, so the generalization that we're going to make is that the delta H sub H of more substituted alkenes is less exothermic. Words are going to come out. Okay, so the delta H sub H of more substituted alkenes is less exothermic. Okay, so smaller delta H sub H in terms of absolute value. Okay, and so what that means, so meaning that the alkene, which is our starting material, is lower in energy. And lower in energy means higher in stability. Okay, so that turns out to be a general trend then. So the general trend that we're going to follow is that the more substituted the alkene, the more stable it is. Okay, so we'll say generally, more substituted alkenes are more stable. And the general thought behind this is a hyperconjugation effect. So where the substituents can interact with the p orbitals of the pi bond. All right, so let's just draw out our trend in stability. Okay, so the most substituted an alkene could be is if both carbons of our carbon-carbon double bond have 2 carbon-based substituents. So in all of these cases, R cannot equal hydrogen. Okay, so this would be what we call a tetrasubstituted alkene. Okay, and it's tetrasubstituted because we have 1, 2, 3, 4 substituents. Okay, so we're going to count the number of substituents. 4 is the max number possible around our alkene, and that's how we're going to determine our substitution. Okay, so a tetrasubstituted alkene is generally more substituted than an alkene where we only have 3 substituents. So one of those I'm going to replace with a hydrogen, and this would be called a trisubstituted alkene. Okay, and then if we take away one more substituent and make it a hydrogen, we have 2 or 3 different ways that we could have a di-substituted alkene. Okay, so one of them would be if the two R groups, the two carbon-based substituents are on different carbons and they're trans to each other. So we'll call this di-substituted, and then we can just say trans in parentheses to indicate that the two R groups are trans to one another. Okay, so that would be generally more stable than when both R groups are on the same carbon. Okay, and that has a special name. So this is still di-substituted overall. So di-substituted, but we call this geminal. Okay, and so geminal is two groups on the same carbon. Okay, so you could have a geminal diol, which would mean you have two alcohols on the same carbon. Okay, or a gem dimethyl group would tell you have two methyl groups on the same carbon. Okay, and then following that, from a sterics standpoint, the cis disubstituted alkene would be less stable. And again, that was because of sterics. Those two R groups can start to interact with each other when they're on the same side. Okay, and that would be more stable than a monosubstituted alkene, where we only have one carbon-based substituent. This would be a monosubstituted alkene. Okay, so you know what? This is the general trend that we're going to follow. So the more substituted, the more stable the alkene starting material. So you'll find some questions in the workbook at the end of chapter 6 that have you assess and rank alkene stability in this way. And this is the general trend that you want to follow. Okay, and this actually wraps up chapter 6. So we finally have finished this marathon of a chapter 6. So we still have a little bit more time in lecture. So what I'm going to do is actually create a separate recording because we're going to start chapter 7 and I will post those two separately. Okay, so this is the end of chapter 6 finally, and we're going to go ahead and start chapter 7. What you want to do to prepare for the chapter 7 lecture is we're going to need our nomenclature packet. So I'm going to pull that out. We're going to work on nomenclature for a little bit, and then we'll jump back into the notes and think about the chapter 7 reactions. Okay, so I'll see you guys all in a little bit for that.